Our project is aimed at helping researchers and people working in conservation better estimate wildlife densities, and to do that much more quickly and much more precisely than can currently be done with manual methods. And the way we're doing this is you set up camera traps in a sample area. A camera trap is a camera that you set up and it'll take pictures of things that move in front of it, so wildlife. And we use that along with like the area sampled, the amount of time we sample, and the number of animals being detected in order to get an overall estimation of the density of that wildlife population. The project specifically is actually focused on understanding or getting an estimate of the distances between the wildlife and each camera trap, because you need that in order to correct for missed detections. Yeah, so the idea is to have artificial intelligence do that so that it speeds up this whole process and you can get wildlife density estimates much more reliably and much faster. You sample for a given amount of time and you observe a given number of animals. And so, I mean, I'm not going to get into like the details of the formula, but that essentially gives you, okay, roughly this amount of animals, this much time, this much space, I can get a sense of the density. With the depths, what happens is like, if an animal is 2 meters in front of the camera, you can be pretty certain you'll have detected it. But maybe you only detect half of the animals that were at 8 meters away, because the scene is there's lots of bushes and trees and things, right? So the actual images that we've been working with, last semester there was a Basque Connections team that did this sort of project, but they were doing more like manual distance estimation in the Duke Forest. So there was like, I think 50-ish different cameras set up in the Duke Forest. And yeah, and those ran for several months and collected oodles of images. So those are the images we're working with. But the idea is you can use it for any like camera trap deployment setup. Okay, how far away means what probability of detecting an animal if there actually was one there. And then you can look at, okay, what did I actually detect? And knowing the probability of detecting based on distance, you can say what was probably actually there. And so now we know what was actually there, how much area, how much time. We put that together, density.
Seeing all this camera trap image is really exciting because there's lots of deer, raccoons growing in the forest. And another interesting is that I become aware of how powerful like this method can be used in the future. That's kind of make me excited, yeah.
I mean, I'm pretty excited about this project. I've been like sometimes working on my own time a little bit, and like, yeah, it's like puzzle solving, which is kind of like what engineering or like computer science research sort of is a little bit. So most things in this project I didn't know how to do before, but you figure it out. Writing the code, if you know what you're doing, isn't very difficult. But like, yeah, so the harder part is, well, what should we do? How do we get things to work, like researching methods, and then I mean, we have to teach ourselves how to write all of these things. Like for instance, we've been working on a user interface and I had to teach myself like desktop application programming.
Really dense, we did a lot of things, but like the result is good. We learned a lot. It's worth it. It's really worth it.
Like, this is the sort of project that I could just work on for fun, and if I can find ways of doing similar things in the future, that would be very nice, because doing fun for work is great. And it is like related to conservation and fairly important, and so it does a good job of like merging my interests. I don't know, it's like also very meaningful, like it has an impact and you can see that you're doing new things.